guarded by armed military police in the humid summer of 1943. A vast construction zone took shape inside the oak-covered ridges of eastern Tennessee, without ever appearing on any official federal map. Master machinists wearing grease-stained aprons turned multi-ton forged steel cylinders on giant vertical turret lathes behind high chain-link fences topped with razor wire. Yet not a single detailed blueprint across the shop floor revealed a finished part number, an assembly diagram, or a clear hint about the ultimate purpose of these machines. Whenever an inquisitive toolmaker asked his supervisor which tolerance he was holding or what weapon his labor served, security guards quietly escorted him off the facility before sunset, revoking his clearance, confiscating his pass, and freezing his pension. Patrol officers inspected perimeter checkpoints day and night. Stranger still was the mysterious cargo arriving under heavy armed escort inside unmarked armored vehicles. America had quietly withdrawn over 14,000 tons of pure silver bullion directly from Treasury vaults at West Point to overcome a critical shortage of industrial materials. Skilled metalsmiths melted that precious metal down, rolled it into continuous thick rectangular conductors, and coiled those bars into thousands of miles of wire for secret machines no civilian had ever seen. Precision craftsmen shaped custom components to tolerances tighter than 1/50th the width of a human hair, all to separate single invisible atoms of uranium-235. Courageous mechanics held the line against extreme technical odds daily, laying the mechanical foundation for an unprecedented engineering effort. Welcome to Rivet and Rebar, the channel where we explore the industrial giants and mechanical sagas that quietly built our modern world. Take a quick moment to hit the subscribe button and support our show if you love forgotten workshop history, heavy iron machinery, and precision engineering craft. Across Europe during the late 1930s, global society was sliding rapidly into total war. Scientists in Berlin shocked the international research community by demonstrating nuclear fission, proving that splitting an atomic nucleus released terrifying physical energy. Military strategists in Washington and London quickly realized that whichever nation mastered isotope enrichment first would dictate the future of human civilization. However, theoretical physics was only one small step toward ultimate success. Turning complex laboratory formulas into an actual working weapon was fundamentally an immense challenge that needed massive infrastructure and unprecedented precision throughout every phase of output. Victory required giant production plants operating in complete harmony. Picture running an industrial shop when steam-driven overhead cranes moved heavy castings and belt-driven engine lathes shaped metal. Natural deposits dug from the earth contain two distinct isotopes, element-238 and uranium-235. Inert particles make up over 99% of raw ore, smothering nuclear chain reactions and rendering the unrefined deposit unusable for weapons. Conversely, the explosive variant accounts for under 1% of native material. Because both atomic forms share matching chemical traits, standard separation methods, acid leaching, or traditional smelting proved completely useless for isolating the fissile fuel. Separating nearly twin units remained an unsolved engineering problem. At the University of California in Berkeley, physicist Ernest Lawrence realized that isolating lighter atomic isotopes demanded immense physical muscle combined with concentrated magnetic force. Rather than working alone in a quiet lecture hall, the professor partnered with veteran practical engineer William Brobeck. The mechanical designer understood how gray cast iron responds to severe shaping forces, how tapered roller bearings handle radial thrust, and how heat distorts hand-scraped machine beds during long production runs. Having started his career sweeping foundry floors, the chief draftsman possessed deep experience in metallurgical analysis and heavy equipment design. Solid metal housings provided structural rigidity under intense cutting loads. Brobeck and Lawrence created early laboratory cyclotrons by pairing forged steel magnets with hand-machined copper vacuum chambers. They recognized that industrial enrichment required much more than fragile glass apparatus. Success depended on heavy machine tool builders, large Midwestern foundries, and skilled machinists who measured work in micrometers. Raw cast alloy provided the ultimate solution. William took the lead in translating experimental lab concepts into sturdy manufacturing units capable of round-the-clock factory operation. Practical shop experience proved immensely valuable compared to theoretical formulas. Mass variance between uranium-235 and element-238 is less than 3 atomic weight units, a difference thinner than a single sheet of paper. To separate them physically, Lawrence designed giant electromagnetic spectrometers called calutrons, short for California University cyclotrons. The core concept was straightforward. Workers converted raw uranium into gaseous compound, heated it inside a low-pressure tank, ionized that vapor into electrical beams, and accelerated those electrically driven streams past strong magnets. As charged particles traveled through the magnetic field, slightly lighter uranium-235 atoms curved along tighter arcs than heavier fragments, landing in tiny collector pockets placed fractions of an inch apart. Precision receivers trapped purified material slowly. Consider the massive physical scale required for this production process. Processing kilograms of fuel instead of tiny lab samples demanded electromagnetic fields of unprecedented size and stability. Engineers designed magnet structures taller than 2-story houses, using solid steel cores weighing over 250 tons apiece. But as designers planned the secret Whitewell facility in Oak Ridge, Tennessee, they faced a critical shortage of raw industrial supplies. Huge volumes of copper were needed for magnetic coils. Yet World War II had claimed every available pound of alloy for shell casings, aircraft wiring, and naval ships. National defense priorities diverted all electrical metal to ammunition plants. Major General Leslie Groves solved this crisis by approaching the United States Treasury Department to request a massive volume of pure silver as a substitute material. Government officials expressed astonishment at the bold idea, dryly noting that their agency measured ingots in troy weight rather than industrial tonnage. Nevertheless, national security overruled administrative habits. Guards escorted over 400 million ounces of precious metal from West Point to the Phelps Dodge plant in New Jersey. Metalsmiths melted the bullion into 400-pound billets. Workers then rolled those castings into continuous rectangular conductor bars with smooth surface quality. Secure convoys transported metallic blocks under heavy military protection. Workers shipped those silver conductor bars directly to Allis Chalmers in Milwaukee, where skilled coil winders shaped them into giant electromagnetic magnets. Every bend required total precision to avoid microscopic cracks, surface burrs, or insulation gaps that could spark electrical arcs beneath high voltage. Simultaneously at Oak Ridge, construction crews built massive windowless brick buildings to house oval calutron loops, designated as alpha tracks. Boring mills machined forged armor plate into thick D gaskets. Toolmakers hand-scraped sealing surfaces of these metal tanks to within 10,000ths of an inch, ensuring vacuum chambers held deep pressure without collapsing under atmospheric force. Careful quality checks kept supply lines running smoothly. Precious wiring entered production. Tolerances remained strict. Throughout November 1943, project engineers completed the first Alpha 1 track at Whitewell and energized the electrical circuits. Tens of thousands of volts rushed into the silver coils, creating magnetic fields so powerful that loose wrenches, steel tape measures, and iron filings flew out of workers' hands, slamming against frame surfaces. Wristwatches stopped instantly, and massive structures groaned under intense force as dense metal cores absorbed tremendous energy. Electric generators hummed loudly as electromagnetic power reached maximum intensity. Sudden disaster struck within hours of continuous operation. Thermal expansion twisted heavy steel frames out of alignment. Vacuum seals cracked along welded joints. Organic oil insulation surrounding the silver coils baked and carbonized under intense heat, allowing conductive carbon paths to form short circuits that caused high-voltage electrical arcs across months of coil winding. The charged beams vanished, bringing the entire plant to a complete standstill and threatening the atomic project. Emergency teams worked continuously to contain arcing damage. Military leaders worried that the entire electromagnetic separation plan had failed completely. However, master toolmakers and technicians refused to give up. Teams of electricians, machinists, and engineers launched an urgent salvage effort, working 84 hours a week amidst extreme heat, steam, and solvent fumes. They disassembled the multi-ton magnet assemblies, washed away carbon sludge, hand-scraped shorted silver bars, replaced damaged insulation with heat-resistant mica, and remachined warped flanges right on the shop floor. Unbroken determination restored essential machinery to full production status. Working alongside the mechanics were thousands of female operators recruited from local Tennessee farms, remembered today as the Calytron Girls. Seated on high stools before tall control panels, these farm women adjusted knobs and switches for 12 hours a day to keep magnetic fields balanced, unaware that their efforts were separating atomic fuel for a war-ending weapon. They endured toxic solvent fumes and electrical fires while repairing damaged units, proving that quitting was not an option for the patriotic crew. Dedicated technicians maintained perfect voltage balance throughout long factory shifts. By spring of 1945, tireless work at the Whitewell machine shops produced outstanding results. Solving the mystery of the silent facility, Oak Ridge had expanded into a massive industrial engine operating thousands of Calytrons across alpha and beta tracks. First-stage units enriched raw feed to roughly 15% uranium-235. Technicians then transferred that material into smaller, highly precise second-stage loops, where toolmakers set receiver pockets to micrometer accuracy using custom collets and dial indicators. Calibrated collector slits trapped refined fissile particles with extreme exactness. Slowly and carefully, the silver magnet tracks refined the fissile fuel to an extraordinary purity, above 89% uranium-235. On July 25, 1945, 50 kilograms of weapons-grade enriched uranium, the entire global supply of nuclear material, was packed into lead-lined containers, secured with official seals, and escorted by counterintelligence officers to California. Flight crews then flew the atomic payload over the Pacific Ocean under total radio silence to Tinian Island. Secret transport routes protected aircraft carrying classified cargo across the sea. That exact 50-kilogram payload of enriched uranium formed the explosive core of Little Boy. The atomic bomb dropped on Hiroshima on August 6, 1945. Without custom vertical lathes, hand-scraped vacuum tanks, silver bus bars, and constant maintenance from Whitewell workers, the Manhattan Project would have been delayed by years. An invasion of the Japanese mainland was avoided because secret manufacturing facilities in Tennessee maintained accuracy standards thinner than a hair. Precision machine shop specifications made nuclear fuel separation physically possible. Reflect on the mechanical victory hidden inside this secret saga. While popular history focuses on theoretical physics and famous scientists, physical reality demonstrates that atomic energy relied on tool steel bits, precision spindles, collet indexers, roller bearings, and cast iron lathe beds. Every atom of uranium that changed human events passed directly through sharp cutters, vacuum tanks, and silver coils at Whitewell. Classified work concluded, mathematics held true, and the mission succeeded. Heavy equipment bases transformed abstract formulas into practical success. Post-war production adjusted rapidly. Early electromagnetic calutrons, though effective, consumed huge quantities of electricity to separate minute amounts of material. Newer, continuous gaseous diffusion facilities like K-25, followed decades later by high-speed centrifuges, provided far more economical industrial enrichment. Within months of victory, operators decommissioned most alpha tracks, turning off the giant silver magnets for good. Advanced chemical processing replaced initial calutron units after historical evaluation. Government officials then executed one of the most thorough inventory audits in industrial history. Technicians unbolted the silver bus bars from magnet frames, cleaned them of grease, melted them down, and packed them into wooden crates. Workers returned over 14,000 tons of bullion back to Treasury vaults at West Point. Final accounting figures showed that less than 1/100% of the precious metal was lost, mostly as tiny dust particles during heavy machining and rolling. Careful recovery techniques preserved microscopic metallic fragments collected throughout production. Decades later, American manufacturing experienced a profound shift. The industrial base that built Whitewell, rooted in massive gray cast iron, long apprenticeships, in-house vertical integration, and durable machinery, was gradually dismantled by corporate financial strategy. During the 1970s and 80s, investment groups and commercial raiders bought historic machine tool makers. Celebrated companies like Cincinnati Millicron, Warner and Swassey, and Allis-Chalmers were broken apart, stripped of assets, or liquidated for immediate dividends. Quality craftsmanship gave way to offshore production, while molded metal was substituted with thin, disposable equipment. As silver returned to vaults and executives took control, short-term paper profits replaced long-term excellence across factories. Yet despite the loss of classic manufacturing corporations, the heavy iron machines of the atomic age refused to disappear. Financial speculators who dismantled American toolmakers retired long ago, but physical cast metal tools built during that era remain operational. Durable alloy outlasted monetary trends. Solid machine tool castings withstand severe shop usage across multiple decades. Visit contract machine shops across Tennessee, Ohio, and the industrial Midwest today, and you will still find 80-year-old vertical turret lathes, surface grinders, and press beds originally constructed for Whitewell. Modern machinists retrofitted these massive castings with digital readouts, optical encoders, and high-speed CNC spindles. Aged gray casting absorbs vibration and resists heat distortion in ways contemporary lightweight steel frames cannot match. Built with extraordinary craft, these vintage tools continue turning aerospace forgings and military parts to tight tolerances. Corporations dissolve and financial empires crumble into dust, but iron outlives the empire. Legendary American machinery continues shaping defense hardware with unyielding precision. Thank you for watching Rivet and Rebar. If you appreciate heavy craft and forgotten manufacturing sagas, please click the like button and subscribe to our channel to discover how another historic industrial giant constructed America's heaviest steam locomotives. Tap the video recommendation on your screen right now.